to guarantee that it can be incremented and decremented atomically. And so the compiler will let you wrap things in an atomic reference count, and then they can be reference counted properly. So let's go back to our source code. Yay, our source code, where is it? It's right here. Here's what an atomic reference count in use looks like, right? I'm going to wrap my random numbers that I generate in an atomic reference counter. And then for each thread that I spawn, I'm going to clone that counter. Remember, cloning here doesn't make a copy of the data. It just increments the reference count to say there's another copy of the data now. I now just get a copy of the ARC data, and it doesn't contain and the data pointer is the same in all of them. And then I move that into the closure with a move closure. It turns out I probably don't actually need the keyword move here. It will move it. Oh no, I do, because I'm going to take the address of that thing, and so I have to make sure it gets moved instead of just referenced, or it won't work. What happens if I don't have move there? Well, what's the lifetime of this rand? It's this iteration of the loop, right? What's the lifetime of the closure? The compiler has no idea, right? It has to assume the closure can still be running when the program exits. So the compiler is going to say, nope, sorry, you're trying to use a pointer from your environment that's going to go away before the thread finishes. In this case, that's absolutely true, right? Each iteration of the loop, you're going to drop that thing you made. So the move closure says, no. When I reference something in the environment, move it in. And now it's actually going to move this rands into the closure, and now the closure owns it, and so now it's going to be safe for it to be there until the end of time. And so our reference counting is all going to work, and everybody's going to be happy, and other than that, the code looks just like it did before, and so now let's see how fast we can do this on the same data. What did I call it? ARC. Here's generating this, calculating the same statistics 16 times. Let us remind ourselves of what the sequential program was on 1. Oh, okay. That's a lot worse. But it's calculating the same statistics 16 times, right? That's completely unfair. What if I calculate sequential 16 times again? Oh, thank you. It does panic. You're right. It panicked both times. My bad. I'm not paying attention to what I'm doing. That's not good. Now that's on 16 different blocks, so this isn't apples to apples. That's a long time. Let's try sequential 1 again, 0.252, and let's try arc 16 again, 0.291. Oh! So it's almost as fast to compute the statistics 16 times using parallelism as it is to compute it once. Whoa. What does that tell us, by the way? What is the biggest source of expense in this program? What? Well, yeah, but the memory usage is roughly the same in both programs, right? Because the sequential 1 is just calculating the statistic. The sequential 16 one shares cache uses and stuff, but basically it's the same memory usage. So what's most of my overhead? It turns out it's not calculating the statistic, it's random. It's generating the random numbers. Turns out to be really expensive, and that's for 2 reasons. One is because random number generators are, especially the default one it uses, are stupid expensive per word generated. And the other one is that memory writes are way more expensive than memory reads. The statistic only reads memory. The block maker thing writes it. Huh. Parallelism is hard partly because there's a lot to think about, right? You don't get to, if you care about performance, you don't get to sweep details under the hood. Professor Karavanik in our department is a world expert in performance measurement and performance analysis, and has a PhD in parallel performance and gets giant grants in parallel performance and runs other PhD students in parallel performance. This is a whole field. You can spend your whole career doing nothing but parallel performance. So be prepared to spend a little time to get even vaguely competent at it. And this is a good example of that. Anyway, let's see what a rayon example looks like. Here's using rayon. I'm going to literally make a bunch of blocks of random numbers in parallel, and then I'm going to literally calculate the statistics on all those in parallel. But you'll notice there's no forks, no joins, there's nothing except this funny par iter. Par iter is in the rayon library. It's an iterator, just like you think it's an iterator. And the cool thing about rayon's par iter iterator is that it runs iterations of your iterator in parallel. It figures out how many cores might be a good number to use, and it will start up all that many cores worth of iterations in parallel as you go. And so you get parallelism for free. Not having to worry about groove closures and forks and joins and blah, blah, so much. You just iterate over your data structure. And here we are, iterating over our data structure to make it, and then iterating over it again to collect the results. Let's see how fast this thing is. Now again, all these are doing incomparable things. I should really, rewrite this benchmark pretty much. But look what's going on here. 0.8 seconds, 4.2 seconds, and a lot has just been swept under the hood. This is a very recommended approach for new Rust programmers who want to exploit parallelism for performance. A lot of people, if you ask someone, just go, oh yeah, just use Rayon. Start with Rayon. If Rayon doesn't solve your problem, then check back, but Rayon will probably solve your problem. It's one of those things. Really easy to use, really reasonable performance. Right, our speed up there isn't, it looks like it's more than 4. I'm taking advantage not only of the cores, but the hyperthreads here. That's kind of
cool. So Rayon will manage, mostly manage, like whether or not it's wise to do parallel?
Yeah, Rayon looks at your CPU and actually tries to figure out how many iterations it should run at a time of this parallel thing. So that's part of what it does, is it tries to make good heuristic guesses about it. Or I don't remember if it does some combination of that and actually checking to see how fast things are running, and I don't remember what. It does a lot of magic under the hood that I don't frankly understand, which is fantastic, because I don't want to understand it. But yes, at the end of the day, it won't just, if you iterate 1,000,000 times, it won't just spawn 1,000,000 threads, because that would be a really, really bad idea. It'll spawn, 8, 4, 16, something like that. So it's kind of like the worker pool stuff, but because iterators are special, because iterators are sort of independent, each iteration's independent, it feels like it can just, I'll just pass this out. Yeah, so I can highlight recommend Rayon, it's fantastic. Crossbeam is what was used in the book example. You could look at that too. I don't think I have a crossbeam example here. Channels are another thing. So, like I say, in Go, the main way that threads communicate with each other is through channels. And a channel is just a notional endpoint. Typically, channels are one way in this world. They aren't like a TCP stream where it's both a read-write channel. You typically make 2 channels for that, a reader channel and a writer channel, which is super annoying sometimes, but that's how it's normally done. And that's how Rust does it. And Rust has perfectly good channel support. They're what's called, when I create a channel, I get 2 endpoints, a read endpoint and a write endpoint, right? Then when I fork a thread, I can move one of those endpoints into the thread when I spawn it. Oh, and now we have a channel. The child thread holds one end, I hold the other end, communication can happen. They implement write and read, like we talked about in I/O recently. And so I can write into the right end of the channel with write line or something, and I can read from it with read line or something. Everybody's happy. I can pass Rust data over it. And I should be really clear, because it looks like there's networking going on. There's no networking going on here. How do you think those channels are implemented in Rust? If you looked in the library code, what would you see? How does the communication happen between the threads? Processor support, operating system support, what happens in there?
Shared memory.
Shared memory, right? Under the hood, it's still the same shared memory mechanism that you were going to use before with mutexes and garbage, but there again, channels hide it for you. Rust's current default channels, although there's some discussion of changing this, are what are called multiple producer, single consumer channels. That means there can only be one read side. You can't have multiple people reading from the channel. Only one person can read from it. But the write side is cloned. I can clone the write side and pass it all over the place. And so there can be many things writing into the same channel. So it's a really convenient mechanism for merging requests from a whole bunch of threads to some other thread. That's a multiple producer, single consumer. What order do they go in? It's unspecified. Multiple producer, multi-consumer is what you'd want if you wanted to be able to distribute stuff among threads, right? Then you can clone the reader side too, and whichever reader read next got whatever one of the things that one of the writers had written. That's cool. There are crates for that. I'm sure go get a crate off crates.io. And there's some talk of merging the best of those crates into the standard library, so that's in place. Let's look at channels as implemented by implementation. So of course I have one of those two. Oops, is this the right thing? No. This is it. Channels. Oh, there's a gotcha that you need to worry about. So we're going to make a new channel. It's really, really easy. We get a send side and a receive side. And then we fork a thread. And what is this doing? Oh, I see. So this thread is going to be the thread that is the consumer of all the random numbers, of all the statistics that are produced, right? So we're going to fork a separate thread that actually receives, I don't know why I forked a thread here, just to show I could, I guess, that actually receives the statistics and prints them all out. Yeah? So each time it does a read, a receive call, and receive is an iterator, which is really nice. Each time it does a receive, it prints the value it received. And then in the sender side, we'll fork n threads to actually compute, make a block of stats and compute its value. Go back to that model. And then we'll send those stats to the receiver thread. And now the only thing we have to do is the same thing we always have to do, which is wait for all these threads to finish. And then we're good to go. So let's try running that, see how fast it runs. What do I call it? Channel? I think so. Oh, it's pretty similar to what Rayon did. There's not much overhead. Not much overhead at all for channels. In fact, you'll notice the user time is actually lower than it is for Rayon, which is kind of cool. And the real time is very slightly higher. That's pretty cool. It's pretty cool indeed. Actually, those numbers there again aren't that comparable because the experiments aren't that comparable. The point is, you don't pay much for this. The channels are very convenient, easy to use, and they will save you a lot of bugs, and they don't cost much. Channels good. Until they are. Until you need something that are awkward for them. You should use them. Here, by the way, is pipeline parallelism, which I don't think I talk about anymore in the slides, so we might as well just run it. Sequential pipeline versus parallel pipeline. Oh, that demo's terrible. I'm not going to show that. So there's some parallelism stuff. This is all on the GitHub if you want to look at all this stuff. Let's keep going here. Here's a thing that confuses everyone when they're starting out in Rust. which is the send and sync traits. Remember way, way back when we talked about traits, we talked about things called marker traits, which are either to communicate information to the compiler, or the compiler is going to communicate information to you typically. Send and sync are marker traits. They're used to interact with the compiler around thread safety. Like I say, every Rust program is a thread-safe program, so you can run into send and sync issues even if you don't think you're doing any concurrency. So you should be aware of that and ready for it. Send is a marker that says, and all these are sort of auto-derived for structs and enums. They're sort of auto-maintained by the compiler. The compiler and the standard library work together to know what should be sent and what should be synced. And your data structures, for the most part, will be send when the compiler can figure out how to make them send, and sync when the compiler and the libraries can figure out how to make them sync. So what you'll typically be is, I need a send value or I need a sync value here. I don't have one, what do I do? We'll talk about some of the things you can do. What do these mean, though? Send says it's safe to move the value to the other thread, that it would literally be okay to take this value and move it, make a copy and then delete the original, right? Move the whole object wholesale into another thread. And you can't move a thing into a thread unless it's send. Oh, and then there's sync, which says it's safe to send a immutable reference to this thing to another thread. And you can't use even an immutable reference in another thread unless it's, from the first thread in the second thread, unless it's synced. And you can't use mutable values in another thread at all. There's just no way to share mutable references to values. Sorry, that's not a thing. Well, if that's not a thing, if I can only share immutable references, how do I use that to have a shared data structure that's mutable between two threads? What's my plan? Is there anything we've heard about in the last week or so that might help me out here? I need to be able to use a mutable reference, but I only can use an immutable reference, so... Yeah, but I need an mut, vectuate, and I only have an I can only sync with an ampersand vectuate, so how do I push onto my vector? Well, how do I get a new reference? What's on here? You have all the machinery in front of you. We talked about it in the last week. What do? Don't make me give that lecture again. I don't want to give it again. It's an hour we can't afford. Reference counts and... reference counts aren't the key thing. What's the key thing? Interior mutability, right? This idea that I can have a thing that looks like an immutable reference, but you can actually change its insides. Now, it turns out that I'll need some special kind of interior mutability to be able to safely synchronously access, right? What do I need? Well, I need some kind of lock, maybe a mutex of some kind, right? Here's the cool thing about mutex, is that a mutex is one of those things that's an interior mutability structure, like a ref cell is, or a cell is, right? Ref cell and cell are not send sync. You can only use them in the thread that owns them. Mutex, it turns out, you can use it in any thread, because when you go to access, when you go to dereference the mutex, it will lock first before it lets you at the insides. Then you can borrow the insides borrow the insides mutably. It's classic interior mutability. Yay, interior mutability. So I make a mutex that's got a usize in it. And before I can change or even read the value in that mutex, I have to call the mutex lock method. And the lock method actually does what it says on the tin. Nobody else, if anybody else tries to call lock while you've got it locked, they will block until you unlock with it. Yeah?
Will the compiler bother you to lock and unlock?
Well, there's no other way to get at the value inside. You literally don't have any direct access. You only have access through the lock method. That's the only way that you can get at it. So yeah, the compiler will be like, I don't know what happens if you didn't call lock. I don't have a thing, I just have a mutex. And so you have to ask, and the compiler will absolutely refuse to compile code that tries to get at the data any other way than by calling the lock method on the mutex. And so you're required to do that, and that's cool. And here's one catch, is that lock doesn't actually return a reference to your value or anything so beautiful as that. It returns a result containing that thing. Here's the weird situation. So I have a bunch of threads running, and one of them takes the lock, and then core dumps right in the middle of modifying the data structure. Right? That's a thing that can happen because it used unsafe Rust code. Right? Yeah? What's the situation? Well, lock mutex is locked. Right? And you're in the middle of the operation that modified the data structure. So you don't want to just right in the middle there get rid of the lock, right? You don't want to just unlock it. Because if you unlock it, who knows what you've got? You've now got a data structure that might be garbage because you've done part of the modifications to it, but not all the modifications. Yeah? So that mutex is marked what's known as poison. Any attempt to lock it will now return an error. And it's up to the process to decide what to do at that point. There's the thing that was trying to lock to decide what to do at that point. There are ways to handle mutex poisoning, but in general, probably that should just end your program if the mutex gets poisoned. You should probably panic. So I can write this kind of stuff. And notice that the star there is a little bit magic.